Hello everybody, welcome to my video on Cobb Douglas utility maximization. This is going to be a calculus-based video. My first one I've actually done like this because none of my classes have used much calculus yet. So this will be helpful for you if you're in an intermediate micro class that uses it, or a mathematical economics class, or maybe even as a guiding example for a graduate level. So here's what we're going to do in this video. I have a utility function, x1 to the alpha times x2 to the beta. x1 and x2 are the quantities of two different goods that the individual consumes. Alpha and beta are both parameters that are greater than 0, and alpha plus beta has to be less than or equal to 1. These are assumptions I'm going to make. These assumptions mean that this utility function is concave, which means concave, whatever, which means I get to have an interior solution. That means I don't have to worry about corner solutions. I'm not going to have to worry about Kuhn-Tucker conditions. I can just set my first order conditions equal to 0 and be good to go. Because of that, it means that this budget constraint here, where our wealth has to be greater than or equal to how much money we spend on the two goods, I can actually now make it be equal to. And that's because of these blue conditions. If I allowed alpha or beta to be negative, making one of the goods bad, or if I were to make the function convex, I might have to start dealing with corner solutions and I'd have to check a lot more. For now, let's not worry about that. Alright, so we got to maximize utility subject to this budget constraint. Let's get a Lagrangian put in here. Constrained optimization always has a Lagrangian, so x1 to the alpha times x2 to the beta. That's our objective function, the thing we're trying to maximize. And then we also are going to add a Lagrange multiplier times the budget constraint set equal to 0. Like so. And that's a Lagrangian function. I'm going to choose x1 and x2 to maximize that. Another way of me talking about these blue conditions over here, these ensure that lambda is greater than 0, which means that the W equals x1, px equals expenditures. But yeah, I don't want to belabor that. That's not the point of this video. Just a sec. So, let's maximize it. Derivative of the Lagrangian with respect to x1 is equal to alpha x1 to the alpha minus 1 times x2 to the beta minus lambda p1, and I'm going to set that thing equal to 0. This is one of my first order conditions. My other first order condition, same exact thing but for good 2, beta x1 to the alpha okay, great. There they are, the first order conditions. Those coupled with the budget constraint give me my solution. Now I want to combine these two equations. It tells me something about the trade-off between x1 and x2. So allow me to sort of cheat here a little bit because this is written digitally and not actually on paper. Let me move this down here as a couple of equations I'm interested in, and I've moved the lambda p's to each side. Then the next thing I'm going to do is, again, kind of cheating because I'm doing this digitally, but you'll get over it. I'm going to now take a ratio of each of these, where the ratio of the marginal utility from x1 over marginal utility of x2, so this is my marginal rate of substitution on the left-hand side, is equal to that. Lambda is the same in both, And this is where your marginal rate of substitution equals the price ratio thing that people talk about when we skip the calculus step. We can simplify this a little bit more, and it's going to be alpha x2 over beta x1 equals p1 over p2. All right. I said we're going to solve for x1 and x2, so let's work on that. X1 is, all right, so x1 is equal to, let's see, p2 over p1 times alpha over beta times x2. And there it is. Don't worry, that was my computer, not yours. So there's a ratio of alphas to betas that will hold in optimum. Now we need to plug this ratio into our budget constraint. P1 times x1 plus P2 x2, and this is all gonna equal, let's see, what is that gonna be? See, the P1s cancel, so this is P2 x2 times alpha over beta plus 1 equals P2 x2 times alpha plus beta over beta. And all that's equal to W. So to solve for the demand for good 2, x2 star, we're just going to isolate that out of this. You can get beta W over P2 times alpha plus beta. Now, I can substitute this into our ratio for x1 is P2 over P1 alpha over beta times x2, but we have something else for x2 now, so times beta W over P2 alpha plus beta. So x1 star is going to equal alpha W over P1 alpha plus beta. Oops. And there you have it. We've solved for our Cobb Douglas x2 and x1. So these are our Walrasian demand functions if your teacher called it that. I can also give you indirect utility functions if I wanted to, where I would say V of P1 P2 W, which is equal to x1 star to the alpha times x2 star to the beta, which is equal to alpha W over P1 alpha plus beta, all of that raised to the alpha times beta W over P2 alpha plus beta, all of that raised to the beta. See, we can combine some like terms here. We'll get W over alpha plus beta, all raised to the alpha plus beta, times alpha over P1 to the alpha times beta over P2 to the beta. So a couple of things we're going to see in these equations. One, our demand functions. They increase as our income goes up, and they decrease with price. And the other parameters are there too. Our utility, what are you going to see here? The more wealth we have, the higher our indirect utility. I guess I'll point at this one, that's the final. And our utility goes down as the prices rise. So all this stuff is all the stuff we tell the intro kids. It's all built into the Cobb Douglas. So yeah, I hope this was useful to you. If not, too bad. Here's where I'm going in my next video. I'm going to expand this into n dimensions. Instead of just 2 goods, there will be any real integer of them. And after that, I'll talk about using these results to build demand curves. So, hope it was helpful. If not, too bad. Thanks for watching, guys. Good luck.